Unlock your digital dreams. This is New Deep Dive.
Imagine an invisible world. Radio waves just permeating everything around us, the atmosphere, deep space, even, our daily lives.
Yet they're everywhere.
And they're not just background noise, are they? They're like these silent whispers from the cosmos. Clues to everything from how stars are born, these huge explosions, to subtle shifts in, say, our own planet's magnetic field.
Exactly. Signals carrying real information.
Okay, let's unpack this. For this deep dive, we're going to tune into these cosmic frequencies. We're talking about Earth's giant ears, these advanced radio telescopes that are really changing our understanding of reality. They let us perceive what was once just utterly invisible. So today, we're kind of embarking on a journey exploring this global network of incredible instruments. We're going to dive into systems like LOFAR, that's across Europe, the huge SKA project. That's the future one.
The big one, yeah.
India's GMRT, Australia's MWA and ASCAP, the UK's E-Merlin, and Tianlai in China, too. Cool. Yeah, our mission, to figure out how these machines work, the amazing tech behind them, the secrets they're uncovering, and, well, why they're just so crucial for science going forward.
And we should probably touch on the other side, too.
Right, we'll also touch on how these powerful technologies can sometimes spark. Well, fascinating, sometimes speculative questions about what else they might do.
What's truly fascinating here, I think, is how these different systems, they all have unique capabilities, unique specialities. They're not just islands.
They connect.
Exactly. They come together. They form this interconnected global network, and each one adds a really crucial piece to the puzzle, our cosmic puzzle.
Okay.
So we'll explain not just what these telescopes are, but why they're such essential windows on the universe. They help us tackle the really big questions, origins, evolution, maybe even life beyond Earth. This deep dive, it's basically designed to give you a shortcut to being really well-informed about this silent symphony of the cosmos, and maybe reveal some surprising things along the way.
Sounds good. So let's start by tuning into Europe's cosmic ears. LOFAR. That stands for Low Frequency Array. Now, when you think telescope, you probably picture a giant dish, right?
That's the classic image, yeah.
LOFAR just completely turns that on its head. This isn't your grandpa's radio telescope. It's the largest, most advanced low-frequency instrument out there. Stretches right across Europe. Netherlands, Poland, Ireland, Latvia.
It's huge.
And it operates at really low frequencies, between 10 and 240 megahertz. Think of it like tuning into the deepest bass notes of the universe, almost subaudible stuff.
And that's where its innovation really shines. Instead of one massive dish, LOFAR is this distributed network. Thousands of small antennas.
Thousands, wow.
Yeah, all working together using something called phased array technology. Imagine having thousands of tiny digitally connected ears spread out over huge distances.
Okay, I'm picturing it.
So this means LOFAR can steer its radio beams electronically, instantly, without actually moving any antennas.
No moving parts for steering.
For the steering, no. It's all digital. This agility is just revolutionary. It lets it observe multiple bits of the sky at the same time, and it's specifically designed to study, well, the early universe and things in our own atmosphere that traditional dishes just can't really capture well.
That digital steering.
Yeah.
That sounds incredibly powerful.
Yeah.
What kind of specific insights are we actually getting from LOFAR, being able to listen to these really low frequencies?
Oh, the insights are profound. LOFAR is like a cosmic time machine. It lets us literally see the universe's first light switching on during the epoch of reionization.
A cosmic dawn.
Exactly, the cosmic dawn. That crucial time when the first stars and galaxies ignited and they transformed the universe from this dark, neutral fog into the transparent, ionized state we see today. It's genuine cosmic archaeology,
Amazing.
And beyond that, LOFAR is also vital for watching the sun. Solar flares, coronal mass ejections, these huge bursts from the sun.
Which matters for space weather, right?
Hugely important for space weather prediction. Because those things can disrupt our satellites, even power grids down here on Earth. It even helps us study changes in our own ionosphere, which directly affects radio waves and satellite comms.
And the data. The amount of data it must generate must be just, well, mind-boggling. I read that each LOFAR station sends this astronomical amount of data to a central supercomputer. Can you give us a sense of that scale?
Absolutely. I mean, each LOFAR station, whether it's one of the dozens packed together in the Netherlands, the Superturp, or an international one stretching way out across Europe, It's a collection of hundreds of these little antennas.
Right.
And all that data we're talking, up to 3 gigabits per second from each station, gets sent via fiber optics to this central supercomputer in Groningen in the Netherlands.
3 gigabits per second per station.
Per station. To put that in context, that's like simultaneously streaming thousands of high-definition movies
Yeah.
from each station all the time. And that processing power is what lets LOFAR create these incredibly precise images of the sky. It gives us an angular resolution, a sharpness that rivals the Hubble Space Telescope, but in the radio spectrum.
Incredible.
And yeah, you're right. It's a massive amount of data to manage, but it's absolutely essential for picking out those incredibly faint whispers from billions of light years away.
Okay, so if LOFAR is the current king of low-frequency radio astronomy, then the Square Kilometer Array, SKA, that's undoubtedly the future, isn't it?
Oh, absolutely. The heir apparent and then some.
This really ambitious international project,
Mhm.
set to be the largest radio telescope ever built, a collecting area like 1 square kilometer. What makes SKA such a monumental leap forward, and how does it sort of build on what systems like LOFAR have already done?
Right, so SKA is the next generation. It pushes the boundaries of sensitivity, how faint it can hear, and the range of frequencies even further. It's actually got 2 main sites. There's SKA Low in Australia. That'll use phased arrays, much like LOFAR, but just on an unprecedented scale, operating at 50 to 350 megahertz, so overlapping with LOFAR but extending a bit higher.
And the other side.
That's SKA Mid in South Africa. That uses more traditional-looking parabolic dishes, but with incredibly advanced digital kit behind them. It operates at higher frequencies, from 350 megahertz up to about 15 gigahertz.
Covering a huge range, then.
A massive range. But the truly staggering part of SKA is the sheer volume of data it's going to process. It's estimated it'll generate more data than the entire global internet traffic right now.
More than the entire internet.
That's the projection. We're talking exabytes of data per day.
That is almost unimaginable. What kind of fundamental questions will SKA be able to tackle with that level of data, that sensitivity?
Well, it's designed to go after some of the most profound questions in science, things like probing the very beginning of the universe, the formation of the first galaxies, similar goals to LOFAR, but with even greater precision. It'll test theories of gravity by watching pulsars and black holes in really extreme environments. It's also expected to be an incredibly powerful tool for SETI, the search for extraterrestrial intelligence.
Looking for signals.
Potentially detecting incredibly faint signals from distant civilizations. Yeah. And it'll map magnetic fields across entire galaxies and even in the space between galaxies, giving us insights into structures totally invisible to optical telescopes.
And European groups, the ones with LOFAR experience, they're involved.
Oh, heavily. European institutes are key partners. They're bringing all that expertise from LOFAR, developing the technology, figuring out how to handle that insane data flow for this huge project.
It sounds incredible. But as fascinating as LOFAR and SKA are, this global network of cosmic years, it extends way beyond Europe, doesn't it?
Absolutely. It's a truly global effort.
What other crucial instruments are contributing to our picture of the radio universe?
Well, if we move eastward, you've got the Giant Microwave Radio Telescope, or GMRT, that's near Pune in India, another global giant.
GMRT, right.
It consists of 30 massive parabolic antennas. Each one is 45 meters across, huge dishes, operating in the 150 to 1500 megahertz range.
Still pretty low frequencies, then.
Meter wavelengths, yeah. It has this unique Y-shaped layout, which gives it long baselines, good for high angular resolution, sharp images. It's a more traditional design than LOFAR's arrays, but GMRT has had significant upgrades. It's still right at the forefront.
And what's its specialty?
It's particularly good at studying neutral hydrogen gas in distant galaxies. That gas is the raw fuel for star formation, so tracking it helps us understand how galaxies evolved across cosmic time.
Okay, so from India, let's head down to Australia. They play a big role too, right? Especially with, say, SALO being there.
Indeed. Australia hosts the Murchison Wide Field Array, or MWA, that's out in Western Australia, in a very radio-quiet area.
MWA.
It operates from about 70 to 300 megahertz, so again, low frequencies. It's a key precursor, a pathfinder for SCALO. It uses thousands of dipole antennas, quite similar to LOFAR's, but spread over a more compact area.
So maybe not quite as sharp a view as LOFAR.
Its angular resolution isn't quite as high, no, because the baselines, the distances between antennas, are shorter. But its location is fantastic. Australia's Murchison region is incredibly quiet. in terms of radio interference.
Less human-made noise.
Exactly, which makes it ideal for hunting those incredibly faint signals from the epoch of reionization, and also for studying solar storms without lots of terrestrial static getting in the way. That quiet zone is absolutely crucial.
Makes sense. And then if you want really detailed, super high-resolution views, we need to look elsewhere, maybe the UK.
That's where eMerlin comes in, based around the famous Jodrell Bank Observatory.
Ah, Jodrell Bank.
eMerlin is a network of 7 radio telescopes spread across the UK. They operate at much higher frequencies, from about 1 gigahertz up to 22 gigahertz.
Higher frequencies, sharper details.
Generally, yes. Its antennas are linked by fiber optics, creating what's called an interferometer with baselines up to 217 kilometers long. This gives it truly unparalleled angular resolution, really, really sharp vision.
And what do you use that sharpness for?
It's perfect for incredibly detailed studies. Things like peering right into the hearts of active galactic nuclei, where supermassive black holes are launching powerful jets of material, or investigating the dense, dusty regions where stars are being born in distant galaxies. It's highly complementary to things like LOFAR. LOFAR gives you the wide, low-frequency view. eMerlin gives you the sharp, high-frequency zoom.
So they work together, covering different parts of the picture.
Precisely. You need both.
And what about other significant contributions, maybe from Asia or elsewhere in the Pacific, besides the SKA site down under?
Yeah, definitely. Back in Australia, besides MWA, there's also ESCAP, the Australian Square Kilometre Array Pathfinder.
Another pathfinder for SKA.
Right. This one features 36 parabolic antennas operating between 700 and 1800 megahertz. And what's unique here is they have phased array technology, but it's located right at the focus of each big dish. It's kind of a hybrid.
Interesting mix.
It's a real workhorse for mapping neutral hydrogen over huge areas of the sky, studying how galaxies evolve, cosmology, paving the way technically and scientifically for SK Mid in South Africa.
Okay. And China. You mentioned Tianlai earlier.
Yes, the Tilan project in China. This is more experimental still, a low-frequency radio telescope working roughly from 400 to 1400 megahertz. Its main goal is to map neutral hydrogen to investigate dark energy.
Dark energy, wow.
Yeah, using a technique called intensity mapping. And it uses an innovative design with cylindrical arrays instead of individual dipoles or dishes. It's a really significant and rapidly developing regional capability for cosmic studies in Asia.
It's truly incredible, isn't it, how all these diverse technologies spread right across the globe each contribute their own unique piece to understanding the universe.
It really is a global collaboration.
But, you know, when you talk about such powerful technologies, ones that reach so far and deal with radio waves, it's kind of natural for a curious mind to wonder about their full potential.
Right.
And sometimes that curiosity, well, it can take us into more speculative territory.
I see where you're going.
There's this common fascination, I think, with how advanced technologies, especially ones dealing with unseen waves and frequencies like these, might have applications beyond just their main scientific purpose.
That's a perceptive point.
Yeah.
The sheer power of these instruments, their ability to detect and process these incredibly faint signals from across the universe, it naturally sparks the imagination, doesn't it?
It does.
And while the primary purpose, the established use of these radio telescopes, is absolutely for astronomical observation, scientific discovery, the discussion around their broader implications, it does highlight that fine line.
Yeah.
Where scientific inquiry meets wider technological potential.
Right.
The ability to manipulate and receive such sensitive signals over such vast distances, yeah, it can certainly lead to some imaginative thoughts, even if they're unconfirmed, about just how far that reach extends.
Okay, so we've just taken this whirlwind tour, haven't we, through some of the most incredible cosmic years on our planet. From LOFAR's amazing low-frequency view across Europe, showing us the early universe, space weather, all the way to the immense power of SKA, poised to generate just unbelievable amounts of data, more than the entire internet.
It's quite the journey.
We've touched on India's GMRT, looking at neutral hydrogen, Australia's MWA and ASCAP pushing boundaries down there, the UK's eMerlin giving us those super sharp high-resolution views of black holes and star formation, and China's Tianlai exploring dark energy.
A diverse set of tools.
Exactly. Each system, with its unique tech, whether it's LOFAR's thousands of little antennas and those clever phased arrays, or GMRT's big, powerful dishes, plays a critical complementary role. They all fit together. And these aren't just telescopes, are they? They're data behemoths, using supercomputers, fiber optics, and more, AI, artificial intelligence, just to process these faint whispers coming from billions of light years away.
The data challenge is immense.
So what does this all mean? Well, it means we're building this unprecedented global network to listen to the universe on scales never before imagined, revealing a cosmos that's far more dynamic, far more interconnected than we ever dreamed.
Yeah. And if we connect this to the bigger picture, these radio telescopes, they aren't merely instruments, are they? They're really our bridge to the mysteries of the universe, letting us perceive what's otherwise completely invisible.
Seeing the unseen.
Precisely. They let us test fundamental theories like gravity, magnetic fields across galaxies, even search for signs of extraterrestrial intelligence, potentially.
That possibility is always there.
And the dedication, of the scientists and engineers behind projects like LOFAR ERIC, the SKA organization, that ensures this journey of discovery is going to continue, constantly pushing the boundaries of what we thought was possible.
Which is exciting.
It is. And this raises an important question. Maybe for you, our listener.
Yeah.
These systems, they allow us to listen to the cosmos. What else might we hear? What deeper questions might those unheard frequencies inspire in you about the universe and maybe our place within it? Are you ready to truly listen to the universe?
Subscribe to New Deep Dive.